Hi everyone, my name is Rafael-Karampatsis, and this is joint work with my supervisor Charles Sutton from Google. I'm going to talk about how often the single statement bugs occur, the ManySStuBs4J dataset. Uh, so in the industry, it's very important to have some sort of tool like a static analyzer with super high precision, more than 90%. What we basically want is we don't want to have high false positive rate because that would waste developer time and it would cause tool rejection because the developers wouldn't want to actually use the tool. So what we want is a sweet spot between precision and recall. This is very important from the industry. So one way to maybe find this sweet spot is to focus on repairing classes of simple bugs. So examples of such bugs are single statement bugs, one-liner bugs, or bugs that fit certain templates like mutators. Yet there is a problem. There is a lack of data for estimating the recall of repair templates for real bugs. So we kind of wanted to fill this gap and create this sort of data. So we defined 16 templates of single statement bug fix changes. The inspiration behind this is that these kind of errors are tedious to spot, yet easy to fix upon realizing where they are. So these are not syntactic errors, they're actually semantic errors. But upon realizing that the developer has done such a mistake, they might call themselves quote unquote stupid. So we named this kind of bugs simple stupid bugs. Thus came the acronym STUBs. And the acronym reflects stubbing one's toe and the pain they kind of feel at that time. So let me walk you through some examples. So the first one is you basically use the wrong identifier, like you have, this can happen by copy-pasting code. So you have similar variables and you basically mix them, or you have 2 or 3 functions with similar names that do similar things, but they're a bit different. So for example, instead of calculate bounding box, we called get bounding box, which doesn't recalculate what the bounding box is. It just gives us a value back. So the next example is the change operator pattern. This one is basically mixing similar operators like and then or, plus and minus. The final one I'll show you is swap arguments. So you have a function that takes multiple arguments of the same type, like strings or integers. So it's very easy to kind of mix the order between those. So how we mine the dataset? So our goal was to mine a large number of actual bug fixes to filter out noise. So we looked into GitHub repos, open source GitHub repos. We classified commits as bug fixing or not by looking at the commit messages and spotting if there exist certain keywords in there. And this method has been used before in other papers with very high accuracy, more than 96%. Then we filter out commits that are delete files, and we kept only commits with single statement changes. Finally, we find the versions of the file before and after a change, a single statement change. Basically, we calculate the ASTs before and after the change, and we fit this into a module that checks if any of the patterns exist. Finally, to ensure better quality in the dataset, we filter out common refactorings like class renamings, function renamings, and variable renamings. Finally, here are some statistics for the dataset. If you're more interested in these, I would suggest to just have a look at the paper. So another thing we were interested in is, okay, so these kind of bugs exist in real code, but how common are they? So we define 2 densities. One looks at the project at the snapshot f, and it's basically the number of lines divided by the number of stubs. So we basically do these, for example, at the final snapshot. This is what we use. And we found out that basically in the smaller version of the dataset, This happens at about 2,000 lines. We can expect a bug about 2,000 lines of code. And in the larger version of the dataset, this happens about 1,600 lines of code. The next density is basically taking into account the whole life of the project, so every line that was added and deleted. If a line was modified, it would count it both as an addition and deletion. And this is divided by the number of stubs that exist in the project. So basically, you would expect, in general, stub to appear every 2,000 to 30,000 lines of code. So they're quite common, actually. The final experiment we did was to see if static analyzers could easily spot stubs. And we used spot bugs, but unfortunately it wasn't very good at locating those, and it could find actually a maximum of 12% of those. But it reported also 200 million bugs. So here's some links if you're interested in the paper or downloading the dataset and the code. That's all. Thank you very much.